welcome back again. This video is an attempt to interpret the numbers from table 19.1, which were derived from example 13.1. Remember that example 13.1 is made up. Right now, this is about process. What follows is three examples from table 19.1. The examples are CAPM with alpha, which is condition 4, the midpoint method, which happens to be condition 7, and the zero-intercept method, which happens to be condition 9. These examples will show how the same data is subject to different interpretations. With different data, the midpoint and zero-intercept methods might correspond to different conditions. Remember, CAPM has a zero-intercept expectation under OLS. PRM leads to a non-zero-intercept expectation under OLS. Zero-intercept in PRM is one of several methods of estimating ideal beta regardless of OLS expectations. Example 20.1, Scenario 4, CAPM with alpha. Example 20.1 represents the volatility effect as it is commonly understood. It is CAPM through the lens of PRM. Since Scenario 4 is CAPM, it is assumed that the measurement of beta is correct. That is, the estimated low CAPM beta equals the estimated low ideal beta equals 0.422882, and the expected alpha is 0%, although realized alpha is 0.77118%. Using equation 19.6a, the perturbation risk estimates are as follows. By similar calculation, according to condition 4, the ratio of the perturbation risks is equal to the square root of the ratio of the ideal betas. The square root of the ratio of the estimated high ideal beta to low ideal beta equals the ratio of the perturbation risks, so the condition checks. The estimated perturbation risks are consistent with scenario 4 with an expected alpha of 0%, but with a measured alpha of 0.77118%. That is, if the expected low CAPM alpha is correct, then the excess risk-adjusted return is also correct. The Sharpe ratios are unchanged from example 13.1 and repeated here. Example 20.1 shows the volatility effect as we know it. The perturbation risks are not used in the solution process since it was assumed that the CAPM beta derived from OLS is correct. However, the perturbation risk estimates, if correct, are consistent with condition 4 and give insight into the conditions that generated the results. Finally, idiosyncratic risk plays no role in the solution. However, idiosyncratic risk is the same for every entry in table 19.1 and is calculated here and in the next two examples in order to demonstrate this fact. Example 20.2, Midpoint Method. In example 13.1, all of the parameters are known as part of an ex-ante model. It's easy to see that the parameter estimates in example 20.1 do not match example 13.1 and are therefore not correct. Some alternate method of estimating the low ideal beta and high ideal beta must be found. Example 20.2 uses a purely mathematical technique that does not rely on knowing or assuming an economic model. In the absence of some compelling theory, a logical estimator for the low ideal beta is the midpoint of the minimum and maximum low ideal beta estimates. The formula for the midpoint estimate is derived here in two lines of algebra. With this formula in hand, we calculate a midpoint estimate for the ideal beta for the low CAPM beta portfolio. Again, using equation 19.6a, the perturbation risk estimates are as follows. According to condition 7, the estimated perturbation risks are consistent with scenario 7, with an expected low alpha of 0.3070%, but with a measured alpha of 0.77118%. The difference, 0.4642%, is the estimated excess return after adjusting for ideal systematic risk. The Sharpe ratios remain unchanged from example 13.1 but are repeated here. Example 20.2 shows that different estimation methods result in different estimates of the underlying parameters. Each estimate is consistent with the market statistics. Because we know the original parameters found in example 13.1 are different from the estimates derived in this example, we know the midpoint method did not give the correct answer in this instance. However, the perturbation risk estimates are consistent with condition 7 and, if correct, give insight into the process that generated the results. Finally, idiosyncratic risk plays no role in the solution. However, as stated before, idiosyncratic risk is the same for every entry in Table 19.1 and is calculated here and in the next example in order to demonstrate this fact. Example 20.3, Zero-Intercept Method. The original understanding of CAPM was the zero-intercept model. If correct, then the estimated low alpha of 0.77118% is the statistical artifact of a misapplied method. The way to enforce zero risk-adjusted excess return for the low and high CAPM beta portfolios is to use zero-intercept regression and set the ideal beta equal to the beta estimate generated from that process, assuming zero average perturbation return. This method will be discussed further in a later video. For now, we will continue with the example. Since average excess market return is 10% and average excess return on the low CAPM beta portfolio is 5%, then the estimated low ideal beta is 0.5 and the estimated high ideal beta is 1.5. Running through the calculations again, according to condition 9, the estimated perturbation risks are consistent with scenario 9, with expected CAPM alpha and measured CAPM alpha equal to 0.77118%, but with zero excess risk-adjusted return as measured by PRM. The Sharpe ratios are unchanged from example 13.1 and are repeated here. Example 20.3 is simply example 13.1 worked backward. Since the standard of condition 9 is met for the perturbation risk ratio, the Sharpe ratios follow this pattern, without there being any excess risk-adjusted return as measured by ideal beta. To complete the example, idiosyncratic risk is calculated. If we did not know that the statistics came from example 13.1, it could not be known which interpretation, example 20.1, example 20.2, example 20.3, or something else, is correct. Each entry in table 19.1 is possible along with every unlisted value between the endpoints. Each is a different interpretation of the same evidence. The problem revealed in table 19.1 is that the observable statistics are the same for each entry, while the unobservable statistics are different for each entry. In the real world, it is easy to find examples where the zero-intercept method gives an answer that is outside the range given by the minimum and maximum estimates for the low ideal beta. Perhaps there is something missing.